Hey there. We're about to drive deep, like really deep, into the microscopic world that's buzzing inside you right now. We're talking about biochemistry, the hidden engine that's powering literally everything you do. And it all starts with a question you've probably never even thought to ask.
Really think about that for a second. How does something as simple as a sandwich or a bowl of pasta become the energy for your muscles to move, your heart to beat, or, get this, for your brain to process this very sentence? It's not magic. It's an absolutely breathtakingly elegant chemical journey.
And we've got a roadmap for that journey. First, we'll look under the hood at life's chemical engine and the universal laws it absolutely has to obey. Then we're going to follow a single sugar molecule on its wild ride as it gets split apart, and we see the incredible energy payoff. Finally, we'll connect it all back to your body's amazing power grid.
So let's kick things off with Section 1, Life's Chemical Engine. What is all this chemistry that makes you, well, you?
You know, when you really get down to it, you're just a walking, talking, thinking collection of chemical reactions. That's it. In biochemistry, it's the science that pulls back the curtain and shows us how it all works. It is the instruction manual for life at the molecular level.
Okay, so before we can actually step inside the cell, we have to understand the rules of the road. See, the energy in your body, it isn't some kind of special, mystical force. It follows the exact same laws of physics that govern everything from steam engines to exploding stars. We're talking about the laws of thermodynamics. This first one is the ultimate cosmic accounting rule. Energy can't just pop into existence or vanish into thin air. So that chemical energy locked away in the food you eat, your body is an absolute master at converting it, turning it from chemical energy into the electrical buzz of a nerve impulse or the kinetic energy of you lifting your arm.
Now, the second law, this one's a little weird. It basically says the universe loves chaos. It's always moving towards a state of more disorder, or what scientists call entropy. The messy room analogy is perfect. It takes effort to keep it clean, but it gets messy all by itself. So, how can our bodies be so incredibly organized? Well, here's the trick. To create all this amazing order inside yourself, your cells are constantly exporting an even greater amount of disorder, mostly as heat, out into the world. It's a cosmic trade-off, and life has figured out how to win.
So how do our cells know which chemical reactions are actually going to release energy? They have a tool for that, a calculation called Gibbs free energy. Now, don't worry about memorizing the equation on the slide. The big idea is that it combines the total energy of a reaction with the amount of disorder it creates to predict if it'll happen on its own. If the answer is a negative number, that's a green light. It tells the cell, go for it. This reaction will give you usable energy. Okay, with those rules in mind, it is time to follow the energy. And for that, we need a hero. Meet glucose, a simple sugar from the carbs you eat. Its very first stop inside the cell is a 10-step process called glycolysis, which, and this is cool, literally just means sugar splitting.
Now, the first half of this journey is all about preparation. You know the saying, you have to spend money to make money? That's exactly what the cell does here. It spends two molecules of its energy currency, a little rechargeable battery called ATP, to sort of rough up the glucose molecule and get it ready for the main event, the split. And this diagram shows that investment phase. Don't get bogged down in the chemical names, okay? Just follow the story. In a few super precise steps, our 6-carbon glucose gets a couple of phosphate groups stuck to it. This makes it really unstable, which is exactly what the cell wants. That instability allows an enzyme to come in and just chop it right down the middle. So now we have 2 smaller 3-carbon molecules. The stage is set. All right, the prep work is done. The investment has been made. It is time for Act 2. This is the payoff phase where the cell starts to cash in on that initial investment and turn a serious profit.
Now, here is the most important part to remember. Every single thing you see happening in this diagram, it happens twice for every 1 glucose we started with. Why? Because we split it in 2. So in these next 5 steps, those 3-carbon molecules are oxidized, which is just a fancy way of saying energy is being harvested from them. That energy gets captured in 2 forms, more of those ATP batteries, and another molecule called NADH, which I like to think of as an energy taxi that's going to drop off its high-energy cargo later on.
And what's the return on our investment? 4! A grand total of 4 new ATP molecules are generated in this payoff phase. Not bad at all.
And the grand finale of glycolysis is this step right here. It's a beautiful little biological machine, an enzyme called pyruvate kinase, that performs the final reaction. It plucks off one last phosphate group to make our final ATP, leaving us with the end product of this whole 10-step adventure, a molecule called pyruvate.
So, let's look at the final balance sheet. Let's do the math. We invested 2 ATPs to get the ball rolling, but we produced a total of 4. That's a net profit of 2 ATP molecules for the cell to use for whatever it needs right away. Plus, we walked away with 2 of those NADH energy taxis, which, trust me, are going to be incredibly valuable down the line.
But here's the thing. The journey of that glucose molecule, now transformed into 2 pyruvate molecules, it is not over. Not by a long shot. In fact, this is where things get really interesting. Because what happens next to pyruvate all comes down to one critical factor. Is there any oxygen around? And this slide shows that crucial crossroads. If there's no oxygen, think about your muscles screaming during an all-out sprint. Pyruvate takes a quick detour through a process called fermentation. It's actually a super ancient pathway, kind of a relic from billions of years ago. But if oxygen is available, pyruvate gets the VIP pass to the cell's main power plants, the mitochondria. There, it enters a much more powerful process called the citric acid cycle, which unlocks a massive amount of extra energy. Turns out, glycolysis was just the appetizer.
Okay, let's zoom all the way back out. We've been talking about molecules, enzymes, ATP, but what does this all actually mean for you, sitting here, right now? Why does any of this matter?
Just let that sink in. This whole process, it's happening trillions of times, every single second, in nearly every cell in your body. It's happening right now, just to power this very moment, to let you see and hear and think. It is the constant silent hum of the engine that is you. That piece of bread is literally becoming the thought you're having right now.
When you look at it this way, the story of biochemistry is just one of incredible, mind-bending elegance. Life doesn't just play by the rules of physics and energy. It has utterly mastered them. We've just seen how it takes something as basic as sugar and through this precise chemical dance, transforms it into the very energy that powers our muscles, our hearts, and yes, even our ability to wonder about it all. It's an amazing reminder that inside every one of us is this engine of life, constantly, brilliantly turning the world around us into the world within us.